Okay, so let's start our meeting, our class for today. Assalamualaikum warahmatullahi wabarakatuh and good morning to you all. So, as what I have mentioned last week, this morning you are going to start with quiz number 7, which is on vibration. So, you have your quiz shown, uploaded in our WhatsApp group, which you can download, and I suppose you have downloaded the quiz by now. Don't forget also attendance. The link for the attendance is given on our chat section here in Google Meet, and also I have also provided the link in our WhatsApp group. So what I will do now is I'm going to explain the quiz to you so that you understand how you are supposed, the way you are supposed to answer the quiz. All right. So I'm going to go to presentation now. Just checking. Can you respond to me? We have here our structure that you want to model. Can you respond to that, please?
Yes.
All right. Thank you. So, yeah, if you look at this structure, this is a kind of a beam or bar frame, okay, which is just a kind of rod. Where this structure is supported at both ends, which is fully clamped, fully fixed. And by the way, this is two-dimensional structure, meaning that uh, yeah, as what you have here. So our job here is your job actually is to perform to do the finite element modeling of this structure with the aim, with the objective is to do model analysis. All right, to do model analysis. You see here. Mhm. Okay, that's the sorry model model analysis. With the idea of for you to obtain the first three natural frequency, meaning natural frequency number one, number two, and number three. So that is the our our aim here. And now the job here is to do finite element modeling, but you have to build two different type of model. Meaning now that if let's say you do bar elements, okay, that's question number one. Using bar element, then what you need to do now is you will build the finite element model of bar elements for this structure here. And the model should be able to obtain the first three natural frequency, frequency 1, 2, and 3. So question number one is very simple. No calculation actually needed. Um, you have to do finite element modeling for the structure, that structure, okay, this structure, and using bar element that will be able to produce that you can extract three natural frequency, frequency 1, 2, and 3. So of course we are talking how many degrees of freedom that you need to provide. But for bar modeling, and what you need to do is you have to do the most simple. So if your answer is not the most simple finite element model, then you are wrong. Most simple meaning that the lowest number of element and nodes. So that's the idea. So that's question number one. For question number two, similar, but now you are going to build the finite element model not using bar, but using frame. Okay, question number one is bar. Question number two is frame. The same objective, but different element that you are going to use. Okay, again, you are going to build the most simple finite element model. If you understand, then you can answer. If you don't understand what I have explained to you last week, then you cannot answer. So that's the first two questions. Question number three and four, okay, still for the same structure, still for this structure again, but now instead of three, you are required, you are going to do for four natural frequencies, okay, four natural frequencies, meaning now that you are going to build the simplest, okay, again, the simplest, the most simple grammatically is not correct. Actually, the correct grammar is actually the simplest. All right, but I still use the most simple. Okay, your question number three and four is going to be the similar to the previous question, but now it is for natural frequency, frequency one, two, three, and frequency number four. Question number three is you are going to build finite element model using bar. And question number four is going to build finite element model using frame. Again, the simplest, the most simple. So in your answer here, you are going to build one finite element model, question number one finite element model for question number two, another finite element model for question number three, and also one model for question number four. So you are going to build four finite element models in total. So that is what you need to do. You have to answer it. Uh, no calculation, as of course you still have calculation in your brain, in your mind, but no hand calculation. So that's what you need to do. You have to submit your answer not later than 8:35. 8:35 to my email as usual. Okay, 8:35. I'm not going to accept submission after that. 8:35 to that Gmail email that you normally submit your answer. Okay, so with that, then please do. And after that, as usual, we are going to start our class after your quiz. Okay. Okay, so we meet again, and we are going to start with our session this morning. We have done that actually, but that's for the quiz. Now we are going to discuss vibration. So, firstly, I would like to discuss the quiz with you, and the quiz is very important to my opinion. That quiz is very important. That quiz on vibration because you learn how to do proper modeling for a certain objective, which normally when you do vibration, what we want to do, number one, the most important thing is you want to know the natural frequency. Normally, that's always what we want to do, to obtain the natural frequency. Um, and when you do natural frequency, the term of analysis that you do is normally what we call as modal, modal, modal analysis. And by using modal analysis, then you can obtain the vibration modes from mode number one, number two, up to whatever number of mode that you want to obtain. And for every mode, as what we discussed last week, you can two things. Number one is frequency, and then of course this is natural frequency, and number two is going to be the shape of the vibration. We call it mode shape. So for every mode, you are going to have two. Those that is going to be natural frequency, and the other one is going to be shape of vibration. We call it mode shape. Somebody raise a hand.
You forget to do the recording, Prof.
Okay, sorry, as usual, I forgot the recording. All right. Mhm. I have to go here. So what we are going to do is I'm going to discuss how to answer that quiz. All right. So now we are in recording mode. I'm going to go to presentation mode now. So this is our quiz, the one that you have worked on this morning. So can you see what we have here?
Yes.
So now what we'll do here is I'm going to show you how actually you will answer this question. Um, you will do finite element modeling. So I'm going to show you that here. So this is the support over here on the right and also on the left. So now the first question here is that you want to build a finite element model of bar elements using bar elements that is able to extract, that we can extract three natural frequencies. That means, okay, first thing, Can you answer me now? If, let's say this is bar, all right. If this is your finite element model, which consists of the node here and also the node over there, all right. So you got two nodes. I give the number 1 and number 2. So you have one element which consists of two nodes. So now I would like somebody answer me how many natural frequency that you can extract from this type of finite element model. Let's say this is bar. Anybody want to answer?
0.
So according to our friend here, it is 0 natural frequency if it is bar. Now, if let's say this is frame, how many natural frequency that you can extract? Just now, the answer for the bar, according to that
0.
still 0. So that is correct answer. That's correct answer. So if you have this kind of finite element model, all right, then you are not going to be able to extract any modes or natural frequency. The reason is you have 0 degree of freedom. 0 degree of freedom. Yes, you have two nodes, so you might uh, have the tendency to say, okay, it is 2, then that means 2 degrees of freedom, and then I can get 2 natural frequency, for example. But you cannot, because these two nodes, those are fixed. The two nodes that you have here is not free because it is a fixed node, being that those are at the support. So meaning that no, you cannot have natural frequency for this type of model. All right. So now anybody that is having this kind of model, then of course your answer is wrong. So now let's answer the question that we have. So let's say question number 1. That means you need 3 degrees of freedom. If you want to, to find 3 natural frequencies, then that means you need to have 3 degrees of freedom. And bar node is only 1 degree of freedom. So you need 3 degrees of freedom. And that means you need 5 nodes. 5 nodes with 2 nodes is going to be fixed. And you have 3 extra nodes. And those 3 nodes is having degree of freedom. So this is the correct answer. This is the correct answer for question number 1, because you have 3 nodes that are able to move. And as you know, every node is only 1 degree of freedom, left, right, left, right, left, right. Let's say this is x-axis, then only a single axis degree of freedom because it is a bar. So this is the answer for question number 1. Now, what about I want to have 3 natural frequency, okay, but now I'm working with frame element. So if your answer is this, meaning the same answer as question number 1, then you are wrong, because this is not the simplest. This is not the simplest model. So for question number 2, the correct answer is going to be what I'm going to show you here. I shouldn't have deleted that note actually. You need 3 degrees of freedom. And as you know, if we are talking two-dimensional frame, every node in frame, just like what you have done in your test number 1, every node can have 3 degrees of freedom, meaning horizontal, vertical, and rotation. So what does it mean? It means only, it means that you need only one node that is able to to move. So in total, you got still 3 nodes over here, but remember, node number 1 and 3, they cannot move. 1 and 3, they cannot move. So only node number 2 that is able to move. And as this is frame, that means this node can move left and right, can move up and down, and also rotation. So this finite element model is going to be the finite element model that you need to show so that you know that you are able to answer question number 2. And now, what about question number 3? Now the question has changed. Instead of 3, we want to have 4. We want to have 4. So now I think it is straightforward after what we discussed just now that you need four nodes. If we are talking about, okay, we need 4 nodes that are able to move. And that node is as what I have drawn just now. So these are going to be node number 2, sorry, number 3, number 4, 5, and of course, we have node number 6. So we have 6 nodes, but only 4 nodes that are free to move. Node 2, 3, node 4, and node. So with this here, then you are going to have a bar finite element model that is able to get the 4 natural frequency. But of course, you have to understand that the motion is only left, right, left, right, left, right for every node. It is not going to do rotation. Is not going to be not going to have the vertical motion. So every node is going to do left, right at various combination. Then you will have 4 natural frequencies. Okay, so that is for question number 3, and this is the simplest one. What about if now we are doing frame? If we are doing frame, then you need only 2 nodes. Okay, let me show you that. I need to erase this. So now we are answering question number 4. We want to have 4 natural frequencies, but now it is frame. Okay, so now that is our node. So over here we have 3 elements now. Don't forget, I forgot to write the element number. When you do your answer, make sure that you also include not only the node number, but also the element number. So now this is question number 4. And this is the answer for question number 4, which is frame finite element model consists of 4 nodes, 3 elements, and 2 nodes are free. So this is the simplest finite element model that you could have for you to extract for natural frequency. Actually, the total of mode that you can extract from here is actually 6 modes. 6 modes. Why 6 modes? Because you have 2 nodes that are free, every node 3 degrees of freedom. So meaning with these 2 nodes, number 2 and number 3, that are free to move, then to have motion, then you are having 6 degrees of freedom. 6 degrees of freedom, that means you can extract 6 modes. And of course, if you need 4 modes, then you can have the mode number 1, 2, 3, and 4. You don't need the mode 5 and 6, but you still can get the answer for the mode 5 and 6, meaning you can still also have your natural frequency number 5 and 6. But what you need, of course, is only 4. But that is going to be the simplest finite element model. All right, so with that here, then that is the way you are going to answer your quiz from question number 1 to question number 4. As I mentioned, it is very important that you understand this aspect of modeling when you do vibration. All right, we are going to stop here, but is there any question from you? Anything that is not clear regarding this quiz? Question? Fine, no question. Then we are going to have our break for 10 minutes, and we are going to start at uh, before, I think, 9:10. Okay, 9:10. We are going to start at 10 minutes past 5. Okay, so all right, with that, then thank you, and I'm going to see you again at 10 minutes past 9. See you. Okay, so let's start again. Sorry, it is quite noisy outside. The place where I live is exactly next to the LRT station, and in front of the window is actually the railway for the LRT. So sometimes quite noisy, but I'm getting used to that. So what we will do this second session of our discussion this morning is I'm going to explain to you the theory of modal analysis and some introduction on vibration for finite element, of course. And then we are going to look at the example, um, which is going to be on the bar structure. So for what we will do this semester, when we talk about vibration, theoretically, it is going to be on bar, meaning that we are not going to talk about the derivation for the finite element analysis of frames or for membrane. Uh, but theoretically, we will discuss bar only. That means that the motion is only going to be left, right, left, right, left, right. And uh, the aspect of vibration which involves lateral motion or rotation, because we are working with bar, for example, or if we talk about membrane, for example, then you can do that in ANSYS. Um, in fact, what we did last week was we did three-dimensional vibration. Okay, three-dimensional vibration um, using shell, three-dimensional vibration using shell for cantilever problem. So you have the tool, you have the knowledge on how to do higher order vibration using frame, for example, or shell, because you have done ANSYS, because we have done the demonstration on how to do it in ANSYS last week. And you have also understand the basic of modeling, finite element modeling for vibration. In fact, you have done the quiz just now, which is basically you do the modeling. But in terms of the theory itself, then we are only going to look at the bar element. And when you do your test number two, ODL test two later, you will have to answer a question on vibration using bar elements. Okay, so that is what we are going to discuss on this second part of our class this morning. So I'm going to go to presentation mode now. And by the way, this is also recorded. Oh yeah, before I forgot to mention, please make sure that you fill in your attendance. The links are given. Okay, can somebody respond that we have here a spring mass system? Can you see that, please?
Yes, Prof.
So when you begin to learn vibration, normally what you are going to see is that picture on the right. So that is normally what you see when you begin to learn vibration, or sometimes we add a damper. So this is the spring, and then we have our damper somewhere. Sorry, the picture is really bad. and the mass is going to be here. Okay, so yeah, either you see what you have here on the left or you see the picture on the right. Depends whether we are talking dam or undam. Remember, we have this term dam vibration and dam vibration. If you have this system on the right and then you apply the force F, okay, remember now we are talking, so meaning the force is going to be a function of time. So meaning the force is not a static force, but because this is vibration, dynamic problem, then the force is also a function of time. So if you have the system on the right here, then that is our equation, dynamic equation. Sometimes we call this governing equation. Governing. Governing coming is governing comes from the word to govern, meaning that this is an equation which is controlling the behavior of the system. So that's why we call it governing equation, or sometimes we call this dynamic equation. And if you have more than 1 degrees of freedom, remember that this here is single degree of freedom. Whether you talk this undam or dam, undam with C, damp vibration with C, which is our damping coefficient. Okay, then we are talking about single degree of freedom. Then this is your equation. Okay, so this is the equation for single degree of freedom. If it is more than 1 degree of freedom, then you have to do matrix notation. Okay, so by the way, if I replace the x with d, then of course now it is going to be md double dot cd double dot kd equal to f. So this is a kind of complete equation. Okay, this kind of complete equation. Okay, and um, let's compare this equation with static equation. So what is static equation? Static equation, that means you don't have motion. You have motion, but we assume it is static, meaning that the motion is, the displacement is fixed, static displacement. It's not a displacement which is a function of time, because if it is displacement is function of time, then you have a dynamic motion or vibration. Uh, because of that, then when you talk about static problem, then you don't have acceleration. Remember, actually x double dot is acceleration. So meaning no acceleration, then this part is zero. When you talk about static, then there is no velocity because it is static. Then that means this velocity is zero. X double dot is acceleration, x dot is velocity. So that means you have only this equation. The equation that I um, circle with that box there. And of course, this x can be d, then it is being kd. And being a static problem, then of course the time is not taken into account. So you have kx equal to f, which is actually our equation. And of course, that f can be replaced by d. If f is replaced by d, then of course you will have this equation. That is d, which is basically the same as x. Sorry for ugly writing. Okay, so you see here that actually what you have been discussing before with me this semester, static problem is a subset, is a special case of dynamic problem if there is no accelerations, there is no velocity, and it is static, not a function of time. Okay, so I hope this explanation give you a better understanding on static and vibration. Okay, so if there is no damping, of course, there is going to be governing equation, and you have learned when you did vibration that the solution of this is a kind of that relation. So what you see here is a second order differential equation. Okay, second order differential equation, and the solution of that equation is going to be what you have here. So you have learned this when you did vibration and also when you learn mathematics. So now what we are going to look at is how we are going to do vibration for structure, and the approach is finite element. So, and as I mentioned before, we are doing bar. So that is the bar element, consists of two nodes, node 1 and 2, and at each node you have displacement and force. But now the displacement is a function of time, and the force is also a function of time. So this is similar, but again, this is vibration. Similar to static, but again, this is vibration, which means that this is a dynamic motion, function of time. Let's talk what are these forces, actually F1 and F2 that we have over there. This is going to consist of two force, actually, static and dynamic. Before this, you concern only static force, but now you have to look also at the dynamic force. What is that dynamic force? Of course, the dynamic force is going to be the inertia force due to acceleration. So that is our dynamics force MA, F equal to MA. And we understand that acceleration A is second order differentiation of displacement. So dou square D over dou T square, that is our acceleration. And D, of course, is the displacement. So that is our dynamic force. And our static force is the same as before, which is going to be KD. So KD is our static force. It means that now what you need to do is you have to combine the dynamic force and static force for you to be able to have this total force. All right. Then for node number 1 and for node number 2, our force as a function of time is going to be F1 and F2. But now our equation is going to be consisting of static force, which is this, and also the dynamic force, which is that one. And the static force is, of course, F equal to KD, and the dynamic force is based on our Newton's law. Okay. Now over here we have M1 and M2. What is M1 and M2? Remember that the equation is actually covering this bar, but now we divide it into two equations at node number 1 and at node number 2. And According to the Newton's law, you need mass. So the mass is going to be the mass of the bar. Only now, for node number one, we have half of the mass. For node number two, we have the other half of the mass. So M1 and M2. M1 is going to be half of the mass. Then this is the equation. And that is for the M2L is of course rho mass density multiplied by AL, which is the volume. Okay, and then we divide it by 2, half for M1 and the other half for M2. So that's why now we have this equation. For node number 1 is going to be this equation, and for node number 2 is going to be that equation with M1 and M2. F1x, F2x is what you have learned before. So now let's move on. This equation, okay, these two equations can be written in matrix. This matrix. So, okay, that equation is the same as this equation over here. So now, remember that F1x, F2x is that equation that you have learned before, because F equal to KD, okay, F equal to KD in mat. Of course, you have to write that in matrix. So this F1x, F2x is equal to KD. Remember that? Okay. And then this here is our Newton's force. M1 multiplied that 1. Of course, it is 0. And 0 multiplied that by that, and then plus M2 multiplied by that 1. So this is simple matrix. So this here is actually representing this equation. Okay. So you can write that equation in compact form like this one. Okay, so this equation over here is the compact form of this detailed equation. F equal to KD plus MD double dot. And this M here is what I call as lump mass matrix. And KD is of course your element stiffness matrix. Okay, that is element stiffness matrix, which is you are familiar. So the K for the KD over here is what you have learned, and the mass M over here is what we call as lump mass matrix. Okay, so now we have our complete equation. So what you see here is actually our element equation. This is our element equation. F equal to KD for static, right? But now it is going to be F equal to KD plus inertia force. And of course, the F over here is going to be a function of time. So another approach to write mass matrix is what we call as consistent mass matrix. And for the consistent mass matrix, you need to use shape function. By the way, for bar, the consistent mass matrix is as what you see here on the right. We don't do that. We don't use that. For your course here, we are going to make use lump mass matrix. So this is our element.